Okay, so let's return to the odds ratio or relative odds, and once again we're going to be comparing two dichotomous classifications, the row and the column classification. So we're still in the domain of 2 by 2 tables. Now, some people prefer to do the odds ratio, and we saw that for case control studies this is wonderful because the relative odds was symmetric about whether we first considered lung cancer amongst smokers or smoking amongst lung cancers. It gave the same result. Now, the other reason for liking the odds ratio is that it also quantifies. It quantifies the relationship. So it quantifies the relationship. It gives us an idea of how big a relationship is there, if it's there. So remember, 1 is the null value. 1 says that there's no relationship. So how far away are we from 1, in other words? And so we can quantify. Are we close to 1? Are we far away from 1? Etc. Okay, so we can treat this odds ratio just like any other statistic. And it's going to vary from one manifestation of a study to another. Can we determine how it varies? For example, can you give me a standard error so that I can standardize this stuff, especially if the central limit theorem holds? So generically, here we go. We've got our 2 by 2 table, and we've got the disease status and along the rows, and then we've got the exposure status amongst the columns. And our odds ratio, we can estimate our odds ratio by getting an estimate of disease amongst the exposed divided by 1 minus that, and then an estimate of the disease amongst those who are not exposed, and 1 minus that, divided by 1 minus that, and then take the ratio of the two, and that's the odds ratio. So we can estimate this. Now, what about the probability of disease amongst those who are exposed? So here are the exposed. What's the probability of a disease? Well, we can estimate that by A over A plus C. So there it is, A over A plus C. How about those who are not exposed? Well, it's 1 minus that, which would be C over A plus C. So there it is, C over A plus C. How about those? What's the probability? How would you estimate the probability of disease amongst those who are not exposed? So the probability of disease amongst those who are not exposed is B over B plus D. There it is, B over B plus D. And how about the 1 minus that? That would be D over B plus D. And so there it is. Now we can cancel out the A plus C's, A plus C, B plus D cancels out with the B plus D, and what we're left with is A over C divided by B over D, or another way of writing it is, there it is, the odds ratio, the estimate of the odds ratio is just AD divided by BC. So it's cute. It's very neat. We can estimate the odds ratio that way. What is super neat is that, no, we don't treat this as a standardized normal variate from our central limit theorem. When you take ratios like this, very rarely do you get the central limit theorem working nicely for you. You typically have to take the logarithm. And this is exactly what's happening here. If you look at the log of the odds ratio, that is approximately normal. So it's approximately normally distributed. The log of the odds ratio, it's approximately normal, with a standard error that we can estimate very prettily this way. 1 over A plus 1 over B plus 1 over C plus 1 over D. So there it is. That's the theory for odds ratios. So, for example, if we go back to our electronic fetal monitoring, exposure and C-section, and remember we found that the p-value was extremely small for this, and we said, oh, there's a relationship here. Well, if we do 358 times 2745 and divide that by 229, 2492, we get that the odds ratio is 1.72. So that's like a 72% increase in the odds of getting a C-section if you are getting electronic fetal monitoring done. Now, was this statistically significant? We said yes. What do we mean? But it was different from 1. Can I get a confidence interval around this? Yes, if I go to the log domain. So let me go to the log domain. So the log of the odds ratio is 0.542. The standard error is 0.089. So this minus 1.96 times that, and this plus 1.96 times that will give me a 95% confidence interval for the log of the odds ratio. So there it is. So a 95% confidence interval for the log of the odds ratio is 0.368 to 0.716. But I'm not interested in the log of the odds ratio. I'm interested in the odds ratio. Well, then take the exponential. So take e to the, and you'll get 1.44. Take e to the 0.716 and you'll get 2.05. So there we have the results. So our odds ratio, our best estimate is 1.72, and the 95% confidence interval is 1.44 to 2.05. And this sits well with our previous hypothesis test because this confidence interval does not include the value 1. Our null hypothesis is that the odds ratio is a 1. So there we have it.